Hello, good morning, everybody. We're just waiting 1-2 minutes to allow all participants to be connected, and then we are gonna start. Okay, so good morning, everybody. Welcome to this webinar. My name is Matteo Giuliani. I am an associate professor at Politecnico di Milano, where we are leading the climate intelligence project that is organized among the organizer of this webinar together with ECMWF. And the topic we are going to discuss today is empowering of decision-making thanks to the development of climate services information systems. So the general structure of this webinar is the one you see here on the slide. So I will first briefly introduce the CLINT project and then hand over to Nils Hempelmann from ECMWF, who will talk into the details of climate services information systems, and then we will later on transition to Michael, who will show you a specific application that we developed as part of this project about the tropical cyclone activities. So about the CLINT project is H2020 funded project by the European Union about climate intelligence. So the use of machine learning for enhancing the detection, attribution, causation, as well, and adaptation design in order to better understand and better manage extreme events. The project is structured around 4 main blocks or elements. One on top here you see is the real core of the climate, what we call climate intelligence, that is the development of advanced machine learning algorithms to improve our ability of processing big climatological data across different spatio-temporal scales such that we derive a better understanding of extreme events evolution. These tools are then used to improve climate science, advancing again detection, causation, attribution of a variety of extreme events, with the ultimate goal of eventually producing an enhancement into climate services. So ultimately better forecasting of extreme events or better climate projection of extreme events that can be used for improving decision-making at different scales. So on the one hand, we worked at the European continental scale, exploring the application of climate services through the water, energy, food nexus, and then on some selected hotspots. And lastly, the fourth pillar of the project is this climate services information system that is the focus of today's webinar. The type of extreme events we have been working on during the CLINT project over the past 4 years includes tropical cyclones, extreme droughts, temperature extremes, so namely heat waves, as well as warm nights, and then compound and concurrent extremes. And in terms of climate science tasks, we focused on improving the detection ability of these extreme events, improving the causal analysis, so the connection between drivers and extreme events occurrence, and then lastly, the attribution of these extremes to anthropogenic climate change. As I was somehow anticipating, we worked at different applications at different spatial scales. So on the one hand, pan-European analysis where we explore extremes in the water domain and then impacts on the energy system and the food system. And at the same time, we then zoom in also into 4 different climate change hotspots that are displaying different characteristics as well as different type of extreme events risks, both in Europe, where we have a semi-arid region in the Iberian Peninsula, namely the Douro River Basin, snow-dependent river basin in Italy, south of the Alps, in the Lake Como region. Then we have river deltas in the Netherlands. And lastly, we have also a non-European hotspot located in the Zambezi watercourse that again includes both risks associated with extreme droughts as well as tropical cyclone along the coastline. So to just make a summary of the project, we can see in this conceptual figure the 4 elements or building blocks that I presented, with the climate intelligence on top, informing climate science on the left, which produce AI-enhanced climate services at the bottom. And all these 3 pillars ultimately produce output that are entering into the climate resilience information systems that we see here on the right. And so with this, I would like to hand over to Nils, who will open the box of climate resilience information systems and better describe the content and the value of these tools. So Nils, I'm stopping here and hand over to you.
All right. So, and I hope that that transition is being made, and that I'm now sharing the screen as well. So we are here at this kind of transition from the science into the service. That at the end of the project, and we are now able to hand over the prototypes that we developed within the climate intelligence project into the Copernicus services, for example, or other climate services information systems as services running under production. And we have here also good guidance, good practice guidance, and how to do that, and how to wrap up scientific algorithms into packages that they are able to deploy into that kind of systems. And yeah, and to do so, we have to kind of stick to certain principles. So the FAIR principles, which are developed for data, but it's now currently also applied for entire services, for entire digital infrastructures. And then in the past, this FAIR principle has been enabled by the efforts in having good catalogs and having the data in a very nice way, and having schemas, metadata, etc. That is still valid, and there's still a lot of effort being put into that approaches. But then more and more with the better approaches of machine readable machine learning and artificial intelligence methodologies, that the current efforts are being shifted and more into the way, so that we have the organization of these digital infrastructures with a focus of AI, and so which is a little bit changing the importance of the different aspects of these FAIR principles. And to move away from the European scale, and that the Copernicus services, which are focusing on Europe, and that or being developed by Europe, we have also kind of the scheme on an international level, which is coming from the WMO, where climate services information systems are being suggested, and how to organize them, how to bring them, and they are organized within the global framework of climate services for the entire world. If you would like to know more about that, the source is been here on the screen. Let's deep dive a bit into the Copernicus Climate Change Service, and I would like to present it also in the way that how it can be enhanced by the outside, by the community. So basically, the climate change service is one of 6 Copernicus services. That we have also the maritime monitoring, the atmospheric monitoring, the land monitoring, then a service dedicated to the security and the emergency management service. We will get a couple of these services afterwards also back in the screens, because they are connected to each other. So they are not separated, with a kind of like in a more or less seamless way, able to shift data and information from one of the services to another. Just to point out a bit of the importance and how the Copernicus services, or climate change service, or C3S in short, is improving and enhancing the society, especially the European society. You're seeing the different sectors which is being touched, and which is having a benefit from the service. And then here on that slide is an example of the ERA 5 dataset, which is an reanalysis dataset available from 1940 up to now, and then also with the forecasting mechanisms that also for the short future. We have it available also in the Copernicus services, or in the climate change service, and stored in the climate data store. You will hear about that in a bit later on. And then just kind of as an example, so the effort, that I don't have the exact numbers, but if you're putting the economic benefits into account, so that it is then the effort being put into establishing these services are being paid off by the benefits of the outcome and of the products. So it is a good idea to invest into that services to enhance the economy. And then that is also kind of in the next sense, that the Copernicus services are supporting the European institutions, and this is an example of the European Investment Bank, which are very interested in the climate impact indicators, for example, the hazards, where are the damages, etc., and how to avoid them, how to establish a resilient society. There are hazard matrices, and that has all been connected, and this is all been supported by the Copernicus services. To shift it a bit further, that ERA 5 is kind of more for the past, and that is a reanalysis dataset, but there are also datasets which are directly dedicated for climate services with the sense of adaptation for the future. So CMIP 5, CMIP 6, or then now currently is the next generation CMIP 7 in the production, that is available over the data stores, over the climate change service, with opportunities of making assessments directly over the interfaces, which is provided by the climate change service. So it's an entire kind of pipeline from the raw data to the information, or in other communities, it is being said as an climate service, and holistic climate service from raw data to the information. And there are various kind of data products, so that you can kind of run your applications directly on the data store, that within the compute capacities, that over Python code, or then also kind of that there's a couple of IPython Jupyter notebooks available that you can also build your own, or then also there are kind of the final graphical products available that you can take for the support of your decision. And to learn about that, and that it is possible to have kind of this kind of webinars, which is one among many, or there are a lot of information also available on training modules and education, as well as also there's always the opportunity of reaching out to the support, that if you get stuck, or as also if you are missing some requirements which would be nice for your daily workflow, and so that is also possible to kind of suggest that enhancements in terms of user requirements, which is probably missing, and that we should enable that into the climate change service. Let's deep dive a bit into that's a bit of the take-home message, and that the climate change service in a nutshell. So it's like the global voice on climate, and that informing European institutions, but then also kind of the international one. It's connected to the IPCC and the United Nations institutions, and that dedicated, focusing on the UN climate policy framework. So there's a special atlas, for example, which is giving a visualization of the data for the IPCC, and that there are data distribution centers which are connected to the Copernicus services. It is informing not only for the future, but then also kind of for the past, present, and then also in different time scales. So we have kind of a seamless service from weather service to climate service, with different data sets or data families stored in the data store, and all these data are available through catalogs, and that most of them is within CCY as an open data, following the open data philosophy of the European Commission. And then, as I said, there are Jupyter notebooks to modify, to assess the data directly and generate the information on demand in the way how you would like to have that. And here there are a couple of opportunities so that you have really good freedom to make your assessments in the way how you would like to have that. And one of the opportunities is being shown then afterwards by Michael. And then, right, there's a team of experts, so it's transparent, and that if you have questions, that there are opportunities of reaching out or also ingesting your user requirements in case of something is missing. Let's deep dive a bit into the infrastructure which is standing behind. So that is kind of the backend service, if you want that, and here that is being kind of can be seen as the climate services information system itself, and so a digital infrastructure. And you see here this iceberg with a lot of kind of components inside, and that the architecture is quite complex, but it is made in a way so that it is kind of sticking to the FAIR principles and enables the opportunity of building your own applications around it. So you see the peak of the iceberg. This is kind of the surface or the APIs, and that you can connect, and then from there you can establish further. You see also in the text written that the data store is not only supporting the climate change service or the C3S, but it's also supporting the CAMS, the climate atmospheric monitoring service, or the European the climate emergency management service. So you see that how the different services are linked to each other, that building upon the same digital infrastructure which is in the background. And that is how it is opened, or how it is kind of organized and structured. So there's a cloud infrastructure layer, and then the data layer, which are kind of connected to several data archives, retrieving the necessary data which is necessary to have in the climate change in the climate data store. And then as further we are going to from the left to the right, and that we have more and more applications implemented. And one of the applications that Mikael is later on explaining that could be kind of part of this interface layer, that you are then in the end as a user not kind of being sacrificed by all the big raw data, but you are getting your information directly in the way you would like to have that. There are multiple ways of entering that, and kind of bringing new algorithms and opportunities of manipulating or kind of assessing the data into these systems. There is the Earth Kit, for example, that you see that as one of the squares at the end, and that, or then also applications as portals or platforms which are being built upon it. And right, so it is an organic growth, so that it is never standing still. So we're constantly, day by day, working on improving that system, and according to the user requirements, which is being collected also systematically to enable or to enhance the system in a way so that the climate change service is always directly dedicated to the user's needs. And you can see here also kind of the FAIR principle. So we have a FAIR score for 76, and so we are working on it, that it's improving. So the idea is to kind of get it as fair as sticking to the FAIR principles as good as possible. And there's always an opportunity of improving that. And AI is more and more playing an important role in reaching the or optimizing the services. And I think here is also an application or an example where you can see that it is being supported, or it is supporting other platforms, European platforms. So Wikio, for example, where you can kind of connect to all kind of Earth observation data that's stored in the climate change in the climate data store, but then also in other data stores. So here the different infrastructures are being connected. It is definitely for sure supporting the climate adapt, which is then coming from also other European agencies, the European the environmental European Environmental Agency, EEA, or GRC, or the ESA, etc. So then here that is being an exchange, and sticking to interoperable systems are a crucial part recipe or ingredient of the recipe. Right. So as a summary, for the climate change service, it's a socio-economical and technical landscape, so very complex, and which is rapidly changing because many people are constantly working on that. And then supporting multiple other data platforms, and if you're building upon it, you need to stick to the FAIR principles, to certain rules, and when you're sticking to that, it is possible to connect and benefit from the entire services which are available. It is a reliable one, it is a trusted data, there is a user engagement with a lot of kind of feedbacks, requests, so that we have the use cases always being addressed. And Yeah, it is built in the way so that that the backends are robust, and that the services which are established are kind of established in a way so that they are running in the future in a sustainable way. And with that, how to kind of bring it, kind of enhance these services, and that the CLINT project has been developed prototypes, and one of these prototypes are the tropical cyclone activity, which has been presented and in a bit by Michael, but there are much more that you can find there, and there is a quite a good documentation around it with the principles and how to build up this kind of these applications in the way. So how how is a description of the rules so that you are sticking to the FAIR principles, and if you are sticking to that rules, then it is possible to establish climate services application packages which are in that organic growing ecosystem. And the other application packages which are coming from the CLINT project are here listed, and that we have also a one for in painting missing values, and that, or another one dedicated to heat waves and warm nights, and that as well as also of the drought vulnerability and causality analysis, all filled in with artificial intelligence. So that is the methodology which is behind that. And then if you're going on the websites, you will find much more application packages in a classical way, not with artificial intelligence. And that if you are interested to take them, then yeah, they are there to be used. And then with that, I'm handing over to Michael, who is giving an introduction to one of the packages dedicated of the tropical cyclone activity. Right, Michael, so the floor is yours then.
Okay, thank you. Yeah, Matteo and Nils for the overview of the CLINT project and also the climate services information systems. Yeah, as Nils mentioned, we've developed several climate services application packages, and I would now like to introduce you to the one that is called Shearwater. So what's the idea behind it? In the CLINT work package behind Shearwater, we wanted to explore whether we can leverage AI to enhance tropical cyclone detection. And so we set out to develop and test a number of data-driven models to see whether they could outperform the state-of-the-art physical models and other benchmarks that we created. Our technical objective was to deploy the top-performing AI model finally in a way that enables users to detect both past and real-time tropical cyclone activity in an efficient and also reliable way. And this is where the birdhouse that Nils just introduced came into play. So now, why the name Shearwater? It's inspired by the seabird, known for its remarkable behavior of flying into the eye of tropical cyclones to escape the most extreme winds. But the name also reflects two key predictors of tropical cyclone activity, namely vertical wind shear and warm ocean waters. And the video that is playing here on the right shows actual bird paths, the colored tracks that you see, and in black you see the storm track. And the birds fly into the eye of a storm where the winds are calmer. And for us, this also serves as a sort of metaphor for how shearwater can help to reduce risks associated with tropical cyclone activity. Yeah, next, please. So, what do we mean by tropical cyclone, or short TC activity? We define TC activity following the approach that is used at ECMWF, where it is the passage of at least one tropical cyclone within a radius of 300 kilometers from a location and within a 48-hour time window. And the cyclone should also have at least tropical storm strength, so at least 17 meters per second of maximum wind speed. And this definition is based on the concept of the so-called strike probability that we introduced at ECMWF in 2012. And to generate this target variable, we use the IB-TRACS dataset, which provides, I would say, the most comprehensive global record of historical tropical cyclone tracks. And the example that is shown here is for Hurricane Irma and Jose on September 10th in 2017. So for each 6-hourly TC position over the next 48 hours, we draw a 300-kilometer radius circle, and the union of these areas forms the envelope of TC activity. But then we need to translate this into onto a 2.5 by 2.5 degree grid. And every grid point that lies within this envelope is in the end considered as tropical cyclone activity. So we have a binary mask that you can eventually see on the right. And this method was applied for a long period from 1980 to 2022 for this study behind it. Next, please. For training and evaluating the AI model, we've focused on 7 regions that are highlighted here by the black rectangles. Tropical cyclones occur in most tropical basins, not in all of them, but in most of them. And the frequency varies. It's not equally spread. And to reflect this, we defined regions where TC activity is relatively high, using equal sizes for the rectangles, so the regions. And the reason for this was to be able to stack the target regions for a combined model, and also, of course, to better generalize during the training of the ML model. So the final regions at 30 degrees in latitude and 70 degrees in longitude. And we also try to keep it close to the tropical belt, with an exception for the North Pacific and North Atlantic. And the final regions that we defined are the Northern Indian Ocean, the Northwest Pacific, the East Pacific, North Atlantic, Southern Indian Ocean, Australia, and the Southern Pacific. Next, please. Thanks. On this slide, you see an overview of the candidate drivers that are known from the literature to be relevant for tropical cyclone activity, because they represent environmental conditions that need to be favorable for a tropical cyclone to occur. And the relevant features that were extracted were taken from ERA 5 reanalysis, which was produced by CSIS. And it includes 850 relative vorticity, so we need an initial storm for this, 700 relative humidity, so we need a moist environment, low vertical wind shear, and warm enough water, so sea surface temperatures, and then also zonal and meridional wind components at 2 levels, upper atmosphere and lower atmosphere, troposphere, sorry, to assess the steering flow, but also a measure for the convective activity, where we used total column water vapor. Next, please. We also tested additional variables like climatological probability of TC activity, as you can see in the table here on the left. We tried to replace outgoing long wave radiation, which is often taken as a proxy for convective activity. We tried some other forcings like latitude, longitude, year, day of year, also past target values, and even up to 40 climate indices, for which you can see on the right side the corresponding example EOF patterns. And so we tried a lot in this, and also tried to treat the class imbalance, because as you can imagine, tropical cyclone activity is highly imbalanced. We also tried to increase higher resolution input data, and that didn't help because we had too many trainable parameters. So we tried different things, and the table here is a qualitative summary or an assessment of all these tests that we did. And the green symbols basically represent the additional drivers that helped improve skill in the end. And as you can see, there were not too many. All features were standardized and cropped to the 7 target regions that I showed before. Can you move on? Thanks. We also tried to test different architectures, ranging from simple baseline machine learning models to more advanced ones, such as the unit architecture that you can see here. And in the end, the unit was the best performing architecture for that task, as it also is for several other tasks. And each input feature was treated as a separate channel, eventually forming a multi-channel input image. And we also experimented with adding invariant fields like geographical location and so on after the encoder stage. So we tried a lot to ingest the data. And this is the final architecture that we used here. As mentioned earlier, we had data from 1980 to 2022. And we split that range into periods for training, validation, and testing. And as usual in machine learning development, such a split ensures that the model is trained on enough data, of course, but also fine-tuned for the performance. And one also needs to hold back some data to do a final evaluation in a fair way against benchmarks, but this has to be done on unseen data. So for training, we used the period 1980 to 2010, and for the fine-tuning 2011 to 2015, and the independent testing was done on June 2016 to December 2022. Next, please. I already mentioned that the unit was the best performing architecture, but that was for the purely data-driven approach, which means that the machine learning model learned the relationship between the ERA5 input data at a given time and the target variable at a future time. Another so-called hybrid approach that we tried is that we extracted the features from the IFS forecasts and fed them into the AI model to only bridge between the feature and the target variable at the lead time of interest in the end. And the motivation for this approach comes from an earlier work which showed that combining physical model output with machine learning can significantly improve weekly tropical cyclone activity predictions on the subseasonal timescale. And we also wanted to test this in the current setup. And this hybrid setup allows us to combine the best of both worlds, basically, to use the skill from the physical model and also the consistency of the IFS model for the input features, and also the skill of the AI model to recognize patterns. Next. Thanks. So having developed and tested all these AI models, the questions remain, can they improve tropical cyclone detection? And I brought you 3 plots showing the prior skill score here for the Northwest Pacific, North Atlantic, and Southern Pacific. And the way to interpret this is the higher the value, the better the model, roughly speaking. And the blue line here is the best performing benchmark, the IFS ensemble. And the yellow line is the best performing AI model using the hybrid approach. Overall, the answer is yes, I would say. We see such improvements, in particular for longer lead times, but there are ocean basins like the North Atlantic where none of the approaches tested could outperform the IFS ensemble benchmark. And but because it is skillful in some basins, this model, this trained model, is then or was then deployed in the shearwater application. Can you click? Thanks. Here you see the input mask of the Shearwater Climate Service app on this screenshot that I've taken, and the process requires 3 inputs from the user. So first, the initialization date must be selected. So yeah, this date serves as the reference point for extracting the input features, and it also marks the starting point for the prediction that is made. But it can also be retrospective, so a date from the past. Second, the user chooses a lead time from a predefined list, and this determines when the 48-hour window begins. So it can range from immediately after initialization, here it would be labeled 0 to 48 hours, all the way out to 13 days ahead. And finally, the user selects the region of interest, which is one of the 7 target regions that I've shown before. And these 3 inputs together then allow the tool to generate a tailored prediction using the underlying AI model. Next. Yeah, so once all the required inputs have been provided, the user simply clicks the submit button and the process runs. And the output is then presented in 2 formats. So first, we provide a CSV table that is generated containing the predicted values at each geographic grid point within the selected region that the user has chosen. And this format is ideal for further analysis or if one wants to integrate it into other workflows. And the second output is that the app produces a PNG image that visualizes the outcome of tropical cyclone activity. And the good thing is this map uses the same color coding as a similar IFS-based product generated by ECMWF, which allows them to easily compare the model outputs. So the user gets the output in form of a detailed numerical data set, but also a visual map that can be used. And you can find the QR codes to the documentation and also the GitHub repo on the left. And yeah, with this, I'll hand over back to Nils, I think. Thanks.
Here is it. Yes, thanks a lot, Mikael, for this introduction. That this was one of the examples of the application packages that we produced in Clin, which are currently now under discussion to implement that into the C3S or data store infrastructures, or in any kind of climate services information system, wherever it is fitting and being usable. But in general, to point out a couple of ideas that concerning harnessing artificial intelligence to enhance climate services. And I guess as you have might seen, that there is a huge opportunity to use that the let's say modern applications for climate services, and especially if it is kind of dedicated for impact-based forecasts or climate risk assessment. So which is the use cases that we just showed. There is also a very strong challenge that the AI-driven tools are extremely quickly developing, and then you have seen or can imagine the infrastructure which is standing behind is very large and complex, and with many people are working on that. So it needs to stay reliable. It needs to stay operational. So implementing AI-driven tools is always needs to be taken into kind of into consideration, and that if you're not breaking the rest of the infrastructures, so that is a big challenge. And then also concerning that the awareness of their scientific limitations, as Mikael has pointed out, that it is working good, but not always in the same way for the different regions, for example. So that that needs to be taken into account or point out as the awareness. And then for the recommendations, especially for the European Commission, that of course the AI tools are supposed to be fostered, and that are going to have being used in the future, especially when they are established as open source tools, so that multiple eyes can have a look on that and spot the opportunities of enhancing them, and to stick to the infrastructures or stay in line with FAIR principles. It is necessary to have standardized methodologies or kind of an exchange of best practices, so that we are kind of having the same let's say grammar of the workflows that we are establishing. And we have a couple of European policy frames. So here is listed the European Green Deal guidelines, the Digital Service Act, of course, and a couple more, so that that needs to be taken into consideration, and that when establishing these artificial intelligence based tools to enhance climate services. And if you would like to read further on that, there's the link down there of the policy brief. And with that, I'm pointing out to two opportunities of discussing that further. So the next one is next month in Mostar and the FOSS4G, the Free and Open Source Software Conference. I'm going to give a talk there on the technical aspects for the ideas of standardization of climate services, and then more on the user side, so kind of communicating information and empowering society by climate services, so bringing information into the society to the non-technical people, to the decision makers, how to standardize that workflow or that part that is being discussed in the project or Climate Europe 2 for European regulations of climate services. And if you would like to participate in the discussion, there is a festival in Belgrade. It is a hybrid one, so if you don't want to travel to Belgrade, it's possible to join online as well, but of course in person is higher recommended, and this kind of aspects are going to be discussed there. And with that, we have reached the end of our presentation here. We have a couple of minutes left, probably for an open discussion. Right, I'm handing back to Matteo as the moderator. Thanks a lot.
Thanks a lot, Nils. Thanks, Miguel, for the very interesting presentation. Yes, we have some time for question. So I would invite participants to use the chat to ask questions, so we can directly read and pick a few of them for our speakers. There is already one in the chat, so Nils, if you want to start elaborating on that while the other participants may think about their own question. Do you see the chat?
I
no.
see the chat.
Okay, maybe, no, I see it, sorry. So to what extent does the C3S incorporate local, indigenous, or community level data? And how are these sources validated or weighted within the broader system?
This is a very interesting question, because the local community or local indigenous community data is especially an aspect also that we're discussing in this Belgrade festival. So it's a kind of hot topic to discuss. And as well as also that the C3S is now more focusing on in situ data, for example, that bringing that, so the local community level data into account. So it is for now too less respected and will increase in the future. Right. Concerning in situ data, that the services from land monitoring service, for example, that dedicated or maintained by EEA, by the European Environment Agency, are more focusing on the in situ data for the local communities. But C3S is improving that as well. Right. Then the second one is uncertainties in climate projections communicated within C3S products. Misinterpretation and policy planning in context. That's exactly also a very a perfect question, and we are addressing that in the Belgrade Festival. That is a topic discussed within the project of Climate Europe 2 to bring the communication of uncertainties into a standardized way. So for the moment, it is still kind of, the uncertainty is not standardized communicated, which is causing conflicts from time to time, or a kind of confusion. And within the context of the Climate Europe 2 project, where C3S is a case study, we are working on an enhancement for the communication of uncertainties. And recommend to join the discussion in the Belgrade Festival.
Maybe I can add one from my side. I was typing, but I can directly ask, unmuting myself. For both of you, I think it could be nice to hear your perspective or your lesson learned during the project. So we have been working together over the past 4 years. So what were the major challenges or obstacles that you had to deal with when transitioning from the scientific algorithmic development, primarily scientifically oriented in a way by the other partners in the consortium, into something that becomes a service?
Yeah, I might start probably speaking generally, and then Michael can kind of probably deep dive for the special use case. It was a challenge of the communication. Or, well, Matteo, maybe you remember that while writing the proposal and talking about web service, it was barely understood by the scientific community. And it is a pretty different work habit, and that if you are working as a scientist or if you're working in an productive service. So it's kind of it's a different approach and a different motivation behind. And then bringing that a line or having a good communication in between took a while to understand each other. And so what is the benefit of that? But by the end, as better the services are being shown and the demonstrations are running, as better it was understood, and now I guess the benefits are pretty clear on the table, so that we can move forward. But yeah, bringing the different communities together is still challenging. Or Mikhail, I don't know if
maybe I can just add from the shearwater perspective. So I mean, we were also 2 institutions involved in developing the scientific part, so that was the first challenge. But I think we managed this quite well. And then, once we had some code that was running locally, I mean, we had the chance to deploy it for test purposes in our DKRZ environment, like in more local environment, and this was useful to do some first steps. But then for the final integration, it really needed several meetings between the people doing the technical stuff and the scientific developers. And but I think in the end it went well. So we also use this shearwater application as like a showcase of how other tools can be integrated in the future in the climate data store. So, but we are exploring the opportunities currently, and try to share our experience also with others.
Okay, thank you very much for your perspective on that. I think we are approaching the end of our allocated time. So if there are no further questions from participants, I think we can wrap up here. Thank you very much to everybody who participated. Thanks, Nils. Thanks, Miki. It was very nice to hear from you. Nils kindly posted the link on the chat, so in case you want to stay connected, just go to our website. The Clean project is approaching its end, but the services will be available online beyond the end of the project, so just stay tuned, and there is all the discussion we were mentioning before about potential transitioning from Clean into Copernicus and ECMWF services. So feel free to reach out in case you have interest, and the material is available on our website. Thanks a lot to everybody, and have a nice day. Bye-bye.
Thank you. Bye.
Thanks.